Hi, thanks for joining me. Today I'm going to be going over problem 2 from week 3 of the Invariants Summer Puzzle Competition. As always, I'll leave a link in the description below to the Facebook page of the Invariants where you can find out more details about the competition. Anyway, this is the problem we have for today. We have p being a non-constant polynomial with real coefficients. Then we define kind of this family of other polynomials, so q and x, and they're defined to be equal to x plus 1 raised to the n times p of x plus x to the n times p of x plus 1, and for n being any positive integer. Okay, we want to show that there exists only finitely many n for which qn has all real roots. So in other words, we want to show that there's some sort of upper bound, so that once we pass that upper bound, so once n is sufficiently large, qn will not have all real roots. So qn will have at least one strictly complex root. Anyway, if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into a solution. Okay, so to start the solution, what we have to do is state and prove a lemma. And this lemma is not too difficult to prove, it just essentially falls from Vieta's formula. Anyway, what is this lemma? Well, firstly, I've taken sort of a generic polynomial which we're assuming has all real roots. So a of x equals ak times x to the k plus ak minus 1 times x to the k minus 1, and so on all the way up to a naught. And of course, we insist that ak is non-zero. So a of x is a polynomial of degree k, and we're assuming it has all real roots. Then I claim that this inequality here holds ak minus 1 squared minus 2ak times ak minus 2 is bigger than or equal to 0. Now, as I said, to prove this, we're just essentially going to use Vieta's formula on this guy here. Firstly, it's a polynomial of degree k, so it has k roots, and all of them are real, so it has k real roots. So we can write a of x like this, ak times x minus alpha 1, x minus alpha 2, and so on all the way up to x minus alpha k like so. Pretty standard. Now what we're going to do is look at the coefficient of x to the k minus 1 in this guy here, which we of course know is ak minus 1, because when we expand this here, we're supposed to get this thing here. So the coefficient of x to the k minus 1 is just ak minus 1, but when we expand it from this guy here, just essentially from Vieta's formula, this is going to be minus ak times alpha 1 plus alpha 2 plus so on all the way up to alpha k. Okay, if you've not seen this before, let me kind of give you a brief reason why this is true. We've got k brackets here, all of them with one single x in, and this sort of minus alpha I term. So if we're trying to look at coefficients of x to the k minus 1, we have to take x from k minus 1 of the brackets, and then from the other bracket we have to take the minus alpha I term, and that's why we get this minus alpha 1, this minus alpha 2, all the way up to minus alpha k, and of course this ak is just from there, like so. Cool. Now let's look at the coefficient of ak minus 2. So, the coefficient of x to the k minus 2, which we know is ak minus 2. This thing here, well, again, it's a similar sort of process. We've got k brackets, so we want to take x from k minus 2 of them, and then take the alpha i's from each of the others. So we've got minus alpha I times minus alpha j, which obviously gives us an alpha I, alpha j. So if we just go ahead and compute that, we'd get that this is equal to ak times the sum from ij equals 1 to k, but I cannot equal j, of alpha I times alpha j. So again, we're taking two of these brackets, two of these distinct brackets, and multiplying the minus alpha I times the minus alpha j together. That gives us the alpha I, alpha j, and because there have to be two distinct brackets, we can't have I equaling j. Okay, so this is our coefficient of x to the k minus 1, and this is our coefficient of x to the k minus 2, like so. Now what we want to do is essentially use the fact that all the alpha i's are real to build this inequality here. Anyway, let me clean up the whiteboard, and I'll continue. Okay, so by Vieta's formula, we just proved these two guys here hold. What I'm going to do is take our first line and just square it. So we get ak minus 1 squared is equal to, and now of course minus ak all squared is just ak squared. Then in the brackets, I'm going to get, alpha 1 plus alpha all the way up to alpha k all squared, which of course is just alpha 1 squared plus all the way up to alpha k squared. Then I add on two lots of the sum from ij equals 1 to k, and I does not equal j, of alpha I, alpha j, like so, just from the distribution formula sort of thing. Now, because each of the alpha i's are real, then we know that when we square them, we're going to get a non-negative quantity, so each of these guys here are going to be bigger than or equal to 0. So this thing here is bigger than or equal to ak squared times just this sum here, so 2 times the sum from I, j equals 1 to k, but I does not equal j, of alpha I, alpha j, like so. But of course, this guy here, if we maybe write this as 2ak squared, write it as 2ak times ak of this guy here, this is precisely ak minus 2, so you can get rid of this thing here and just write ak minus 2, like so. So get ak minus 1 squared is bigger than or equal to 2ak times ak minus 2, and of course this just gives us ak minus 1 squared minus 2ak, ak minus 2 is bigger than or equal to 0, just as we want. Perfect, so we've shown the inequality we want to. Now what we want to do is go back to our original problem with the p of x and the qn of x and show that that inequality breaks for sufficiently large n. Anyway, let me clean up the whiteboard and we'll get onto that. Okay, so I've rewritten down what qn of x was, so it's x plus 1 to the n times p of x plus x to the n times p of x plus 1. And I've also supposed that we write p of x in this form here, so very standard polynomial form, pm times x to the m, and so on all the way up to p naught, and of course pm is non-zero, so p is a polynomial of degree n. Cool. Then qn of x is this guy here, or so I claim, and now it's not too difficult to prove this. This is literally me just plugging this definition of p of x here into this guy here, and you get this ugly monstrosity here. But we only actually care about the first few terms of qn of x, sort of the highest order powers, so I've only written those down, so it's 2pm times x to the n plus m, plus, in square brackets, n plus m times pm plus 2pm minus 1 times x to the n plus m minus 1 times what's in this square brackets here times x to the n plus m minus 2. So in this square brackets we have n choose 2 plus m choose 2 multiplied by pm plus m plus n minus 1 times pm minus 1 plus 2pm minus 2. So a big mouthful, but this literally just comes from plugging this into here, but I didn't want to save, I didn't really want to do this on camera because I'd probably mess it up and B, it's very boring to watch. But this is what you get when you just plug in P into this guy here. We only care about the first few terms because what we want to do is show that for sufficiently large n, qn of x has does not have all real roots. And the way we're going to do that is show that for sufficiently large n, the inequality we just derived in the lemma we just had does not hold true. So in other words, so for sufficiently large n, we want to show that the thing in this square brackets here, when we square that and subtract off two lots of this thing times this square brackets here, for sufficiently large n, that quantity will be negative, and that will suffice in proving what we want to prove. However, we could do that, and that would be very, very long and very, involve a lot of unnecessary computation, because here we've got a lot of terms, especially if we're squaring and multiplying and looking at different values of n and m. But remember, m actually is fixed, because m is sort of whatever the degree of p is, and p is given to us. We don't have any choice in what p is. So that means that m is fixed. And remember this thing here, we're only varying n. We're making n bigger and bigger, and we want it to pass some threshold and show that that inequality becomes less than 0. So we only really need to consider varying n. And if you just have a look, this is when we do this, this thing squared and then subtract off this two lots of this thing times this thing, it's just going to be essentially a quadratic in n with a bunch of these m's, pm's, pm minus 1s, pm minus 2s floating about, but they're all constant, so that's fine. So if we want to show that that sort of polynomial in terms of n is, for sufficiently large n is negative, that's equivalent to proving that if we look at that polynomial in terms of n, if we look at the leading coefficient, if that's negative, that's it, that's the same thing, it's equivalent. So what is firstly the degree of this polynomial of n? Well, when we look at this thing here squared, well, this is a linear term in terms of n because you've just got n times a constant. So when we square that, that's going to be a quadratic in terms of n. Then we're subtracting off two lots of this thing here, which is just a constant, times this thing here in the bracket. And here we've got an n choose 2, so that's n times n minus 1 over 2, so that's a quadratic in n. And here we've just got linear terms, so that's fine. So we've got a quadratic minus a quadratic, so that's just going to be a quadratic, or at most a quadratic in terms of n. And if we just look at the leading order coefficient of that quadratic, if it's negative, then we're done. Then that means that for sufficiently large n, our polynomial qn of x will not have all real roots. So let's just look at that. So we only need to consider the coefficient of n squared when we multiply this out. So when we do this thing squared minus two lots of this thing times this thing, we're only interested in the coefficient of n squared. So the coefficient of n squared from this guy here will just be pm squared. And then we're going to subtract off two lots of 2pm. So two lots of this thing here multiplied by the coefficient of n squared in this thing here. Now this thing here is just n squared over 2 plus, minus n over 2. But we're only interested in the n squared over 2. So a half times pm. So times a half pm like so. So when we do this thing squared and minus two lots of this thing times this thing, I realise this is a mouthful, I apologise. But this thing squared minus two lots of this thing times this thing is quadratic in n squared, and the coefficient of n squared is this guy here. Now very clearly half times 2 cancels, and this PM and PM are brought together to give us a PM squared. Like so, we've got PM squared minus 2 PM squared, which of course is negative PM squared. And now we know PM is non-zero, and we also know it's real, but that was kind of written in the question that P has all real coefficients. So that means that this thing here is strictly positive, and then when we put the minus sign in front of it, it's strictly negative, and that proves our claim. Whew. That was a mouthful. This part here was just very ugly and a lot of computation, but hopefully it all made sense. Anyway, thank you for watching. I'll catch you in the next one. Have a great day.